Okay, if you're here for the retake review so that you can get a better grade on your test. There will be some questions along the way, but this is not a quiz itself for a grade. It's just a review. And the questions you see will be there only to help you keep focused and make sure you're thinking about things right. The first 6 questions are going to deal with graphs, where you're given a graph of one world, maybe a distance time world, and you're looking for the corresponding graph in a velocity time world, something that's telling the same story. And you might also have a distance time world and have to tell the story in an acceleration time world. So I would suggest that you pause the video for a moment and then try to answer these before we see any possible solutions, and then there'll be we'll do little one-step quizzes along the way, and at the end we'll check and make sure you're on the right track. So go ahead, pause, and try to see what would be the correct answer for each of these and see if it matches one of mine. Pause. Okay, let's see how you did. I want you to select the correct one of these 3. One of them is much better than the others. Select the correct one from that. Select the correct one from that. We'll call this first one choice A, choice B, choice C, so on down the line. And we're going to insert a quiz in here. And now let's see how you did. Here's how your thinking should go. You should be saying to yourself, I know that the slope of the distance graph is velocity. And so you want to be looking at that slope. That's a flat line. You're going neither up nor down, so that's got a slope of 0. And that has a slope of 0. And that has a slope of 0. And we don't start seeing positive slopes until right here. Gradual at first, then steeper, maybe a slope of 2, and even steeper still. So you're looking for a velocity graph that goes zeros at first, and then bigger and bigger velocities, because we're steeper and steeper slopes. So if you can see the slopes, which we've argued many times the slopes are the velocity, then you just chart those and you should get the corresponding velocity graph. So the correct answer to this one was B. C is not a bad choice because we've got a flat velocity, but it's just not flat at 0. And we had a 0 slope here. This is not a great choice because you've got a changing velocity here and you don't have a changing slope. Let's take a look at the next one. Here we should see ever increasing slopes. It's handy to write the slope right on there. Here's a small slope like a 0, then maybe a 1, then maybe a 2. And then after this we've got negative slopes. Negative, maybe -2, -2. So helpful to just write the slopes right on there. And then you can see which one goes from 0 to 1 to 2, nice and steady. Oh, this guy. And then suddenly drops down to steady negatives. There it is, choice A. And the other ones, this one's close because it does have an increasing velocity, but it never quite gets to a negative slope. It only goes to a 0 slope there. So that would be probably the best second guess. And then finally, let's take a look at this last one. Oh, this is different because we're going to acceleration. Remember, acceleration is the rate at which the slopes are changing. We're looking at how the velocity is changing. So let's take a look at these slopes. Slope of 1, slope of 1. Maybe I'm just estimating here. But they're all the same. So that's the velocity. 1, 1, and 1. Is that velocity changing? No, that velocity is staying the same. So if the velocity is staying the same, that means you're not accelerating, and so we're looking for a graph that has 0 acceleration at the beginning anyway, and that means B and C are both candidates. And then after that, suddenly we have slopes that begin quite negative, like maybe -4, but then less so, maybe like -2, and finally maybe like -1. These numbers are actually getting bigger. They're moving to the right on the number line. If you think of a number line, positives on this side, negatives on this side, we started at -4 and we went to -1. Bigger and bigger numbers, so that means our velocities are getting bigger. That means we're accelerating. So between B and C, this one shows negative, decelerating. This one shows positive, accelerating. So the correct answer was choice C here. So if you had B, A, C, you're on the right track. Let's see if you've got it now. I'll give you one more chance to try your skills. Here's some velocity and acceleration graphs, and we're going to have to find a similar story: velocity to acceleration, velocity to distance, and then acceleration to velocity. Give yourself a moment or two to try to draw them out first. Just go ahead and pause, and then see if they match what I draw in here in a moment. Okay, let's see how you did. Let's take a little quiz and see if you can match the correct one. This will again be choice A, choice B, choice C. See if you can answer these next three correctly. And let's see how you did. So for the first one, we start again. This is the same relationship between velocity and acceleration. The slope of a velocity graph tells us the acceleration. So if we know that slope, then we know that acceleration. Change in velocity, change in time. Rise, run. So if we've lost velocity every moment, we're decelerating. It's a nice steady deceleration. Look at that slope. I'd say a -1, then a -1, then another -1, never changing. So there's our one, choice A, with negative. Let's take a look at the next one. Here we're going from velocity to distance. This is the reverse process. So you have to think to yourself, I am going at one steady velocity of, I don't know what number it is, but it's above 0. It might be a steady velocity of 2, let's say. That means for this first segment, I need to see a distance time graph who has a steady slope of 2. Does that have a steady slope of 2 to correspond to a steady velocity of 2? Nope, that's a steady slope of 0. That's a steady slope of 0 as well, right? Because that's still flat. Look at that slope. Slope is 0, velocity is 0. But we don't have velocity of 0, we have velocity of 2. So we're looking for something with a steady slope of 2. Here it is. Nice and steady. Then what happens to the velocity values? They start climbing. What happens to the slope values here? They start climbing too. From 2 to 3 to maybe 4 to maybe 5. So in the same way that you looked at the slopes of the distance and went to velocity, since it's a multiple choice test, you're going to be able to look at that distance and say which one of these slopes maps on nicely to my velocity. Okay, these are complicated. Believe me, they are one of the trickiest things we do all year long. Very abstract. Let's try one last one. Here we've got a steady acceleration, never changing, but it's positive, so that means we're going faster and faster and faster. Well, here we're going faster and faster and faster, so that's a candidate, and it's a nice steady rate. Look at how steady that increase in speed is. That looks like the same slope. Again, mark the slopes on this graph and then look back there and see if they match. Slope of 1, slope of 1, slope of 1, slope of 3, slope of 3, slope of 3. matches that perfectly. 1, then maybe later on, steady slope of 3. The others have changing slopes, so we would have changing accelerations, but these are nice steady accelerations. So the correct answer here is A. The first one was A, and the middle one was C. Should have had ACA. All right, well, let's move on. Okay, the next 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 questions all revolve around a graph that looks something like this. It's a distance time graph. It's got some curvy spots, it's got some flat spots, it's got some slanted spots, and I simply ask you to think about the velocity and the acceleration and whether it's positive, negative, or 0 in each region. I'll just go slow through this and see if you get them as we go. Let's begin with velocity. The question you should be asking yourself is, really for both of these, is what's happening to the slope? So before we think about the velocity and acceleration, how about if we just become an automatic slope machine? This looks like a negative slope, would you say? Maybe negative 4. I'll only do a few of them here. Negative 2. 0. I'm just guessing, but you can see it's a positive slope going uphill here. This is a steep part. Imagine walking across these. Very steep. Oh, then a nice flat 0, 0 flat spot, steady 0 slope. Then we go downhill, maybe a negative 2. And what happens a little bit later? Still the same slope, negative 2. Then there's a super steep spot, maybe a 3. Gradually less, finally a 0. The story of these slopes will tell us the story of the velocity and the acceleration. Let's begin with the velocity. So in this region, what kind of velocities do we see? Lots of different ones, but they're all negative. How about in here? What kind of velocities do we see? Lots of different ones, but here they're all positive. We're going uphill. Here we see only one kind of velocity, and it's 0, steady. Here we see only negative velocities. We're going downhill. And here we're climbing uphill again, and we're going upward, so that's bigger, or all positive velocities. They're various velocities, but they're all positives. Acceleration's a little trickier because we have to look what's happening to the velocity. Is our velocity getting larger or smaller? So think of a number line again, going from -4 to -2. That's an increase. So that means our velocities are increasing. That's positive acceleration. Here our velocities are still increasing. More positive acceleration. Why don't you do the next 3 zones? Pause. You should have said 0, 0, and negative. Let's make sure you understand why. No change in velocity. That means no acceleration. Still no change in velocity. Is that velocity changing? Nope, it's stuck at -2. So that means you're just going one speed. If you're going one speed, your speed's not changing. That means you're not accelerating. And finally here, look at those speeds. Definitely changing, and changing toward the -3, then 2, then 0. Getting less and less. So hopefully you had all of those correct. You'll see a question very similar to this on the test. Okay, the next 3 questions involve figuring out some numbers for the speeds, not just whether they're positive or negative. So I'm going to ask you, what is the speed of this first segment of the trip? What is the speed of this second segment of the trip? And what is the speed of the entire trip on average? See if you can figure those out right now. And you should have remembered that this speed is the slope. That's our prevailing theme here. And so let's figure out the slope of each of these segments, see how well you did. Slope is rise over run. We can look at any segment of this whole stretch, but I'm just going to look at the biggest segment. My rise goes from 4 to 12. That's an increase of 8. And my run goes from 1 to 2. Rise over run, 8 over 2. That's a speed of 4 whatevers. Let's say that these were meters and those were seconds. So 4 meters per second. For the next segment, you should have had a rise of, that's from 12 to 16, that's a rise of 4. A run of 1, 2, 3. Rise over run, 4 over 3. That's a 1.33 slope. 1.33 meters per second. And finally, for the whole thing, we want to imagine what's the one steady speed we could have held
meters.
starting at this location, ending at that location, that would have got us there just as quick. So I could go fast and slow, I could go slow then fast, but we want to go one steady speed. We want to go that speed. Whatever that speed is, that's the one we're looking for. Let's calculate its slope. So I want to see, we got a rise and a run to figure out here. And you should have a rise, let's see, that's from 4 to 16, that's a rise of 12. And a run from 0 to 5, 12 over 5, that's a slope of 2.4 meters per second. Okay, let's move on from there. Okay, you can really think of this test as being 3 completely separate sections. There's one section on understanding graphs and how distance, velocity, and acceleration are related, and we've dealt with that. Then the next section is about word problems using our equations of motion. And then finally there's a small section at the end where we have some sort of a race and we model that motion with our equations of motion. So graphs are complete, check. And now we're on to word problems with equations of motion. The first 1, 2, 3, 4 questions are going to deal with a problem that has some similarities to this one. Imagine we've got a ping pong cannon, and so we have some fuel in here. We light a little spark, and the ping pong ball, which originally is sitting here all wadded up at rest, shoots out through an 80 centimeter tube and comes flying out with an astonishing speed of 100 meters per second, and your job is to find the acceleration. Let's see if, given what you see right here in front of you, you can do that. And I'll give you a moment to think about that. And now let's talk about the solution. Okay, so we need to think about all of our variables. Our initial velocity, since the ball was at rest, should be 0. This velocity that was given here must be the final velocity of our event. Our event begins, the acceleration is happening inside the tube. It begins here, and the event ends there. Initial moment, final moment. We're not out in the air here, so the acceleration is not going to be 9.8. There's going to be some enormous acceleration of that ball while it's in the tube. We don't yet have any starting distances established, but let's make a coordinate system. We can call our 0 distance right here and here, and so our initial distance then would be 0 because it's right there at the origin. 0, and our final distance would be 80 centimeters, but of course we cannot use centimeters. We have to turn those centimeters into meters, and you might remember that there are 100 centimeters in a meter, so that means that we would have to convert that by dividing by centimeters. 100 centimeters are in 1 meter, so there's our conversion factor. Top and bottom are equal, so we haven't changed the number 80 yet. And the centimeters cancel. 80 times 1 divided by 100, 0.8 meters is our final distance. 0.8 meters. And now we need to choose an appropriate equation of motion. So since we have no information on time, we have to use equation 4, Vf squared equals Vi squared plus 2a times the distance final minus distance initial. And we should be able to put in all the values we have from above directly into this equation and solve for the a. So let's do it. Final velocity is 100. 100 squared is 1 with 4 zeros, so 10,000. Our initial velocity must be 0 since we started at rest. 0 squared is 0. We've got 2 times our unknown a, and our d final minus d initial would be 0.8 meters minus 0. 0.8 minus 0 is 0.8. Notice how I use the meters, not the centimeters. We can multiply the 2 times the 0.8 right now and call that 1.6. 1.6 times a. Plus 0 is still 1.6a. We still have the 10,000 over here. Divide both sides by the 1.6 and we get a number like, can't do this in my head, but fortunately I have a calculator nearby. Let's type that in. 1,000 divided by 1.6 equals, you should have ended up with 6250 meters per second squared. If you got that, you'll probably get all the questions related to this on the test just fine. Okay. Next question. Okay, this next question connects to 6 questions on the test. It's not identical, but similar. We have a jumping bean, and I'm not sure. I think there's some like little weevils that live inside of them, and as they wiggle around, the bean jumps up in the air. But let's say that the bean goes in the air for 0.16 seconds, so a little bit more than 1/10 of a second. And I have 2 questions for you. What speed does it leave the ground with? Question A. And then once we know that, we can figure out how high the bean gets. Question B. Why don't you try to figure those out right now and give me your answer, and then we'll discuss them. Okay, so you should have, if you were successful, you should have had a speed of 0.78 meters per second for the speed that it left the ground with, and you should have had a height, how high it jumped, should have been 0.031 meters. So if you got those 2 answers, you can just go on ahead to the next question. But if not, stick around and we'll discuss this in detail. Okay, so the first thing we want to do is decide on what our event is here. And so we're looking for the speed, and this first part, the speed that it leaves the ground with. So our event must begin here, our initial moment. And the speed, and we can pick any spot along the way for the ending moment. There's 2 likely candidates. You could go up at the top here, because we know quite a bit about that top spot, or you could go at the bottom. Either of those will work, because we know that the going up speed here will actually be the exact same speed here, but just negative going down. So you could use this as your initial, and this is your final. This is your initial, that is your final, your choice. I am going to use this one because it's most similar to how the flow of the test goes. So let's see, do we know this final velocity up here? I would argue that we do. At the top it must have 0 velocity, because for a moment anyway it's neither going up nor down. How long does this event take from initial to final? Well, the whole event is 0.16 seconds, so just this left side must be half of that, or 0.08 seconds here. So that's the time, 0.08 seconds. We've got a unknown initial velocity, that's what we're trying to solve for. And do we know the acceleration throughout here? Yes, we do. The acceleration is equal to negative 9.8 meters per second squared, because presumably we're on Earth. So we can write that down. This is our t, and our a, minus 9.8 meters per second squared. I won't write the units here. The units, though, all are matching. We don't have any unit issues in this problem. So we're going to try to pick an equation that gives us that initial velocity. We know a, we know t, we know v final. The perfect one is equation 2, vf equals at plus vi. Diagramming the problem, identifying the initial and final spots, super helpful. Final velocity 0, let's put it in. Acceleration, negative 9.8 while it's in the air. And the time that it's in the air, we argued, was 0.08 seconds. 0.08 seconds. And we're trying to solve for the initial velocity. And so let's see what happens here. If we multiply the 9.8 times the 0.08, we get negative 0.78. And that's plus vi equals 0. Add the negative 0.78 to both sides, and we end up with our answer that vi equals 0.78 meters per second. Now let's address the question of how high the beam jumps. We can use this result if we want to help us figure that out. Here we can use either of our two accelerated equations that have distance in them. So it could be either equation 3 or 4. I'm going to use equation 4, I suppose, because I know my initial and final velocities. I'll keep the same moments there. So we're going to try to find that final distance. Let's say that the initial distance, let's call this our origin down here, we'll say the initial distance is 0. And so we can write our equation 4, vf squared equals vi squared plus 2 times a times the distances subtracted, so that's df minus di. That's our df minus di. That's our good equation. Let's take a look at our picture. Our final velocity at the top here is still 0. 0 squared is still 0. It's so nice when you have a picture and you label all the key spots. Then you just have to fill in the blanks. Our initial velocity, we said, is 0.78. We'll be squaring that because that's what the equation says to do. Plus 2 times our acceleration, which is minus 9.8, because presumably this beam is on Earth. Our initial distance, we argued, was 0, so that goes away. And our final distance is that thing that we're trying to solve at the top. Okay. Let's see, here we want to start moving things away from our unknown. That's our unknown there. So this guy is going to stay where he is. And first thing we want to do is square that 7/8 and then move it to the other side. 0.78 squared, I believe, is equal to 0.6084. And then when we move it to the other side, it becomes a minus, minus 0.6084, 0.6084, subtracting that from both sides, equals 2 times 9.8 right here is negative 19.6. And I'm pretty sure that if you divide both sides by negative 19.6 right now, you get, indeed, 0.031 meters. Oh, and I'm a bad man for getting my decimal in the wrong spot. I apologize for whatever anguish that caused you. Let me erase that. Erase all traces of my mistake. So apologies for that. But at least we caught the error. Okay, so those are our two values. Let's go on to the next problem. Actually, that's 0.031 meters. We just saw that mistake at the very end, but now it's fixed. This next problem is our last of the word problems with the equations of motion. It goes something like this. There is a frog on a bicycle who spies a juicy looking fly off in the distance. He's already traveling at 3 meters per second, slams on the brakes so as to decelerate at a nice steady rate and arrive at the fly. And the goal is to find the deceleration. So he starts at 3 meters per second. He ends up here at rest, where he enjoys the fly. And your job is to find the deceleration. Give that a shot. Pause, and then come back when you think you have it. And let's see, if you got it right, you can move on. The correct answer was 0.045 meters per second squared. That's what you should have got. Let's see how the solution goes. So let's see if I can get back. Okay, I guess I'm just going to have to reveal the whole thing all at once. So let's take a look. Our initial distance, we're set up our normal variables here. Our initial distance, if we set up a coordinate system here, could be 0. And our final distance is 10 meters downstream, so those are our distances. Our starting velocity, this is our initial moment here. This is where it all begins. This is where it all ends. In our initial moment, we had a velocity of 3, but we ended up at rest, so we had a velocity of 0, time unknown. That kind of forces us into equation 4 because that's the one that doesn't need time. Our starting distance is 0, as we argued, based on our choice of our coordinate system. And our final velocity is also 0. So we have 0 squared is 0, 3 squared is 9. Move the 9 over to the other side first. Multiply the 2 times a 10, get a 20. Divide both sides by 20, and you should end up with that as your answer. Okay, we are now ready to move on to the final phase of our review. We've seen a bunch of stuff with graphs. We've worked through a few word problems. Finally, let's take a look at a race and modeling motion with our equations of motion. Okay, our last one is a race that goes something like this. We've got one motorist that's got a steady speed, already going, V average, that's that little bar there, and he's got a head start of 16 meters, but he's not accelerating, he's just going at one speed. Meanwhile, there's another guy who is all fired up and ready to go, but he's starting from rest, but he's got a sizable acceleration, about half of gravity. And it's only a 42-meter race. So not even half a football field. But this guy's quite a ways already there, and he's already going. So first let's just think, before we do any equations here, let's think about what the graph's going to look like for each of these guys. This guy's starting from rest, so his starting slope will be very low because he's got no velocity to begin with. But then as time goes by, his velocity will get faster and faster, so his slope steeper and steeper and steeper. The other guy will be going at one steady speed, so he'll only have one slope. But he will have a head start, so instead of starting at 0, he'll start up somewhere higher, and so he should go at some steady slope. And where they meet, I don't know, but those are the two motions we're trying to model here. So the first question is, of our 4 equations of motion, which one is best to use, 1, 2, 3, or 4, for the hot rod? And then also, of our 4 equations of motion, which one is best to use to model his motion, 1, 2, 3, or 4? And hopefully you answered that this guy needs to have an accelerated equation, so he's going to have the d equals 1/2 at squared equation, 1/2 at squared plus initial velocity times time. But what is the initial velocity? Well, it says he starts from rest, so this whole term is going to just disappear because 0 is the initial velocity. Let's show that killing off right here. And then also there's going to be the possibility of an initial distance. That's part of the equation. But he's starting from the origin, so that also is going to go to 0. So both of those go to 0. They're gone. And so that's the correct equation to model him by. This guy, on the other hand, is going at an average speed, so you should have chosen equation 1 for him, d equals vt plus d initial, and there is a d initial here. Okay. Our next question is going to be who wins? So that means we want to see when each of these two guys crosses the 42-meter mark. See if you can determine that now. Who does win? Who crosses the 42-meter mark first? And hopefully you have answered that the hot rod does. Let's show why. His equation will use 42 equals 1/2 times a, which we said was 5, times our unknown t squared. We can calculate that t. Half of 5 times 1/2 is 2.5. And if we divide both sides of the equation by 2.5, so we get 2.5 t squared here and 42 here. Divide both sides by 2.5. 42 divided by 2.5. 2.5. I'm on my calculator now. That's 16.8 is equal to t squared. So if I want to know just what t is, I have to square root both sides, and the square root of 16.8 is 4.09. 4.098. 4.098 seconds. That's for the hot rod. And then for the slow guy, but the steady guy, again, we'll put a 42 in for him. And his velocity, we said, was 6. The average velocity times the time, that's t, unknown right now, plus the head start plus the initial distance of 16. So we're going to solve this for t, subtract 16 from both sides. 42 take away 16 is equal to 26. And so that just gives us 6t on this side now, because 16 minus 16 is 0. Divide both sides by 6. 26 divided by 6 is equal to 4.33. And you can see indeed that the slow guy crosses a bit after the fast guy, or the accelerator. Seconds. Okay. The next question that you're going to encounter is at what time do they pass? So it must have happened somewhere around in this area here, just before the 42-meter mark, because now the accelerator is out front, and he's never going to get caught by this guy, but he must have just recently passed because he started behind. And this is going to be phrased to you as a multiple choice question. So you're going to have some choice times when they might have passed. Let's put some choice times in here. That's all going to be nice whole numbers. So we could say maybe at the 2-second mark, at the 3-second mark, at the 4-second mark, the 5-second mark, the 6-second mark. Let's say those are our choices: A, B, C, D, and E. At what time do you believe they pass? I'll give you a moment to think about that, but before you do, let's consider the idea of instead of trying to solve for the time, you can actually put these, since it's multiple choice, you can put the times back into the equation and see which time predicts both the guys having the exact same location. So let's take a moment, think about that. A, B, C, D, E, and hopefully you chose time equals 4. Since if we put a 4 into this equation, a 4 into here, we get, I'll just write it out here, D equals 1/2 times A, half of 5 times t squared. If we put a 4 in here, we end up with a D of 40. And if we put a, so that's for the hot rod. And then for the slowpoke, if we put a 4 in for his equation, let's write that over here, D equals 6t plus 16. If we put a 4 in here, we get 24, 6 times 4, plus 16, and that also is 40. And so at time equals 4, they're both at 40. So that's kind of a sneaky way to solve the problem, just by putting in the answers and seeing when the distances match. It's legit. If you wanted to be a little bit more of a purist, you would set this D equal to that D, and you'd end up with an equation that looks like 1/2 times 5t squared, that's for our accelerator, equals 6t plus 16. This is a little bit of a nasty problem to solve because we've got t squareds, t's, and regular numbers, and that's going to end up needing a quadratic equation or perhaps some clever factoring along the way. If we set it up in standard form with a 0 on this side and everything else on the other, well, we would have a negative 2.5t squared. That's from multiplying the 5 times a half and then subtracting it to the other side, plus 6t plus 16. That doesn't look easily factorable. It probably can be, but you could just turn to the quadratic equation with that as your a term, that as your b term, and positive 16 as your c term, and solve for it there. Okay, that covers the test. You should now be officially ready for it. Good luck when you get there, and I hope this has been useful for you.